Live from Laurel, Maryland, this is NASA's coverage of the double asteroid redirection tests planned impact with asteroid Dimorphos.
In a galaxy where asteroids have pummeled planets for billions of years, now one planet strikes back. For the first time in our planet's history, NASA will test an asteroid deflection technique. It's the first planetary defense method of its kind. NASA's double asteroid redirection test will intentionally ram itself into an asteroid and alter its orbit forever. At the crossroads of science fiction and reality, DART is part of our plan to defend planet Earth against potential future impacts. The test to protect the future of our planet takes place today.
Welcome, and thank you for joining us from Johns Hopkins Applied Physics Laboratory, home to the DART Mission Operations Center. I'm your host, Tahira Allen with NASA Communications, and tonight we're following the real-time journey of the DART spacecraft and its planned collision with asteroid Dimorphos. The Double Asteroid Redirection Test, also known as DART, is the world's first planetary defense test mission of its kind. At 7:14 p.m. Eastern, it will demonstrate an asteroid deflection technique known as kinetic impact. Rest assured, this is only a test. The asteroid DART intends to impact is not a threat to Earth now, nor will it be after the collision. We have live views of the action from space, so keep an eye on the DART cam in the lower left-hand corner of your screen. Right now, you're only seeing a black screen with a single point of light. That point contains two asteroids in it, Dimorphos with a smaller asteroid named Dimorphos orbiting around it. As long as we continue to receive these live views from DART, we're going to keep that feed up on your screen. As we get closer to impact, the asteroid will begin to take shape, and eventually Dimorphos will fill your entire screen. You'll also notice a countdown clock indicating how close we are to impact, and a progress bar that will check off key milestones along the way. Now, as we follow pre-impact operations, we invite you to join us as we check in with Mission Control for live updates and track DART's final milestones. We'll see two astronauts demonstrate what kinetic impact looks like in space, and we'll go behind the scenes at one of the observatories following DART's impact from Earth. You can participate in today's show tonight by submitting questions for our experts to answer live on air. Drop them into the stream wherever you're watching, or use the hashtag #PlanetaryDefender on social media. Now, we're a little over 70 minutes out from impact at 7:14 p.m. Let's now meet your co-host, Samson Reiny, joining us live from the Mission Operations Center. Samson, it's good to see you. How does it feel to be in the middle of the action tonight?
Hey, Tahira, I am feeling great. It is awesome to be back here after co-hosting DART's launch just 10 short months ago. How's the energy over there?
Wow, that's amazing, Samson. You know, everybody's super excited. I've been talking to some scientists and engineers before the show, and it's really just anticipation about what's going to happen tonight. So with that, could you give us an update on how things are going with mission operations?
I'm glad you're enjoying it there. This is going to be fun. So I mentioned launch, right? It was a huge event. NASA launches have become a staple of life for space aficionados. But there's never been anything like what we're about to see tonight, an attempt to impact an asteroid in near real time, the first attempt to change the motion of a celestial body. Just wow. If we hit that asteroid, Tahira, I think we're going to see a whole new side of this team that we've never seen before. Because let me tell you, since launch, these engineers and scientists have been eating, sleeping, and breathing this mission. This center has been like a second home for them as they've been monitoring the spacecraft's health and managing everything from propulsion to the power supply, guidance, and navigation. The list goes on and on. They've run countless simulations and have rehearsed for this moment time and time again, preparing for anything, and I mean anything that could possibly happen. A quick recap of the last 24 hours. No surprise here, they've been busy. Last night, they performed the sixth and last of what are called trajectory correction maneuvers to aim DART to within 200 meters of Dimorphos. Then they worked straight through to this morning to make sure that all went smoothly. Then they soldiered on to get us ready for tonight. And here we are, about an hour and 10 minutes from impact, and we're now in what's called the terminal phase, meaning that SmartNav, the autonomous navigation system, is actively guiding the spacecraft as it was designed to do for its final 4 hours. I also received word minutes ago that DART has reached another critical milestone. Draco, the eyes of SmartNav, is able to detect Dimorphos. This is a major goalpost, I have to remind you, because up until now, Draco has only been able to detect Didymos, the much larger asteroid it orbits. The next major milestone we're waiting for is for SmartNav to be locked on or targeting Dimorphos. We'll get more into what that means later. Lots more to come as we draw closer to impact. Back to you, Tahira.
All right. Thank you, Samson. It feels good to know that we are detecting Dimorphos. Now, before we get any closer to impact, let's get to know our spacecraft and its mission. After a beautiful launch from Vandenberg Space Force Base on November 24, 2021, DART has traveled over 400 million miles. And now, in just over an hour, we'll witness the spacecraft collide with asteroid Dimorphos in an attempt to change its orbit forever. The DART spacecraft is about the size of a vending machine and uses hydrazine thrusters for propulsion and roll-out solar arrays for power. It's traveling at about 14,000 miles per hour and will complete the last 4 miles of its journey in just 1 second. DART is on a collision course with asteroid Dimorphos, which is about the height of the Washington Monument and, more importantly, poses no threat to Earth. Dimorphos sits within a double asteroid system and is the smaller moonlet asteroid orbiting its larger companion Didymos. DART has just one instrument on board, and that's a Draco camera, which is feeding images to its autonomous navigation system, steering it straight into the asteroid. Now, teams from around the world have worked hard to get us to this moment. Samson is standing by with NASA's head of science and Johns Hopkins APL's head of space exploration. Let's check in to hear more about the journey.
Thanks, Tahira. To help give us some insight into what it takes to imagine, much less attempt, a mission this ambitious, I have with me Thomas Zurbuchen, Associate Administrator for NASA's Science Mission Directorate, and Bobby Braun, Space Exploration Sector Head at Johns Hopkins APL. Thanks. Gentlemen, thanks so much for being here.
Thank you.
Thomas, I'll start with you. The mission, this team has been through an intense journey, years in the making, and they're now on the cusp of doing the seemingly impossible, impacting a tiny asteroid 7 million miles away from Earth with a spacecraft traveling 14,000 miles per hour. Why is it important for us to continue to push the boundaries of what's possible in space?
You know, what I always think is the world is made out of a box. Those are things we know that we can use, and a large space of things that are unknown. In that large space are solutions for problems of the future. There's new research, new understanding of nature. And we at NASA, we're all about moving that boundary back, moving it back to make more things useful for us, like DART, but also understanding nature in a new fashion.
That's incredible, Thomas. Well, based on what we know tonight heading into this main event, you know, what are you thinking about our chances of impact?
Wow, I'm betting on the team. Betting on the team is always the right thing to do when it comes to NASA missions, whether it's this one or other teams we've had. The thing you just announced, you know, that kind of seeing that little bump there in the image of that new kind of celestial body we knew was there, but now we've have it on the camera. It's just a step in that direction. I'm very optimistic.
That's awesome. What the team has planned for months, years ago is coming to fruition, and we're watching it live.
Absolutely, it's just exciting.
Awesome, thank you, Thomas. Bobby, you've been through so many white-knuckle experiences with space missions, most recently with the landing of the Mars Perseverance rover just last year. What is the mindset of the team coming to such a major moment in their career with the stakes being so high?
Well, teams like this prepare for the worst, but celebrate the best. And I think we're going to have one of those best nights tonight. There are, of course, many things that could go wrong in spaceflight, but so far this team's been on top of every possible problem. They've been ahead of it, and they just need to focus and push through and go for success.
That's awesome. I think from what we're hearing, the cheers coming out of the mock before this broadcast, I feel like we're on the right track.
Oh, yeah, absolutely.
Any pep talk or advice for the team heading into tonight that you gave them?
Well, I've been in the mock several times today talking with the team. They're calm, they're cool, they're collected. I basically told them just follow the data, trust in each other, trust in themselves. You know, they've prepared for this moment for years, and so they know this better than anybody. And as a team, they're going to get through this successfully.
That's awesome. Thank you both. That's great words of wisdom for moving forward in space, and seems like the team is in good hands with themselves. All right, Tahira, we're attempting the once unthinkable, but the team has prepared for this moment. Now to keep a steady course on this last mission-defining leg. Back to you.
All right, thanks, Samson. I mean, it is incredible what the teams are pulling off tonight. This is a first-of-its-kind mission, testing a way to one day save our planet from a hazardous asteroid. Now, we asked astronauts aboard the International Space Station to show us how this technique works in microgravity, and they had some fun with it. Now, before we get to the video, I urge you to keep a close eye on Shane. He's going to be in the blue shirt and standing in for asteroid Dimorphos. A white object is about to come crashing into him. That's our spacecraft. You'll notice how the impact of the crash moves Shane's position in space. This demo, much like DART's test, relies on the energy transfer from a collision to change the motion of an object. The method, which is called kinetic impact deflection, is the technique DART will test at 7:14 p.m. Eastern. Let's take a look.
So what I'll do, Shane is going to be the asteroid, and I'm going to be the NASA DART mission. Or this CTB, more exactly, is going to be the spacecraft. I'm going to try to throw it, and we'll look at the effect of that mass coming at him and the kinetic energy transfer from the CTB to Shane. Shane will be perfectly stable. It's not an easy task. You ready? All right, here it comes. I've redirected Shane successfully. Pretty good.
All right, now back on Earth, we're taking your questions live in just a few minutes. Send them in using the hashtag Planetary Defender and stand by. It's time now for our first status poll update. Let's head to Samson to check in on DART's progress. Samson, how are we looking?
Hey, Tahira. We are entering the 60-minute mark until impact, and as you noted, the team is about to conduct a poll, which is essentially a status update to check that key systems are in working order. We're talking Draco image quality, smart nav, guidance and navigation, ground systems performance, everything that's anything to do with getting us to impact. All right, I think the poll is about to get underway. Let's start to listen in. We are waiting for that poll to begin any second now.
Smart nav 1 off console.
Waiting on that first poll of the evening. There will be 2 polls, one at 60 minutes, which is now, and one at 30 minutes. Afterward, we should be hearing from Elena Adams, the mission systems engineer, to give us a summary of what we'll have just heard.
All right, folks, we're an hour prior to impact. Woohoo! And we're seeing Dimorphos, so wonderful, wonderful. All right, let's do our poll. Image quality? Let's start with you.
Images are looking great. Dimorphos is coming in at about the same relative dimness as Didymos, so very consistent brightness between the two. And it's a stable track.
That's awesome. All right, Smart Nav.
Smart Nav is looking good. We're sitting at about 30 meters of projected miss distance. There is no movement right now on the bars for doing a maneuver, but we do expect that when we transition in about 10 minutes that we'll see a maneuver at that point.
Yeah, that's great. And at this point, because we have a stable track, we do expect to transition over
That
at
is
that
correct.
time. So that's really good. Whew, that's good. All right, GNC.
GNC is nominal. We're ready to burn.
That sounds good too. And maneuver. All right, let's see. Autonomy.
Autonomy is nominal. Heaters are cycling and no more fault rules.
All right, DSN.
DSN looks good, and we don't see any sign of rain, and ESA looks good as well.
That's good. And then ground system.
Ground system is nominal, and we have a clear vision of Dimorphos on the image display now.
Yes, it looks great. Thank you, guys. All right, one more poll after this, but in the meantime, we're going to hopefully transition at 15 minutes to locking. So stand by.
All right, we're going to hear from Lena ourselves to give us a update.
This is Lena.
Hey, Lena. How's it going?
Good. How are you?
Good. That sounded like a great poll. Any words about what we just heard?
Oh, we're very excited. We are starting to see Dimorphos for the first time. It is looking great. It is just about the same dimness as Didymos as we expected. And so we are getting ready to transition. We have a stable track at this point. It's about 7 pixels in size. And yeah, we're ready to go.
It's great news, Lena. Thanks so much. I'll let you get back to it.
Thank you.
Wow, that was a great update. Joining me in reacting to that bit of news is Angela Stickle, planetary geologist and a DART investigation team lead. Angela, you just heard the poll, you just heard Lena. Things seem like they're going really well. What are you feeling? What are you thinking?
Oh, I'm so excited. This is fantastic. We can see Dimorphos, and we're on our way.
Gosh, basically we just gotta keep humming along, right?
Right.
It's awesome.
Heading in.
Gosh, well, let's quickly talk about the next major milestone that's ahead of us, locking on target with Dimorphos, which could happen as early as 10 or so minutes from now. Right now, SmartNav is still targeting Didymos, right? But locking onto Dimorphos means, all right, Dimorphos, you are bright, you are consistently bright enough, I'm ready to start targeting you. Can you dive into what that means a little bit more?
Yeah, exactly. So SmartNav is looking for bright parts of the image. And so as Dimorphos gets closer and it's brighter and bigger, SmartNav will just target onto it as opposed to Didymos, and we'll be on our way to impact.
That is awesome. Thank you, Angela. That's very cool stuff. Good luck with the rest of the evening.
Thank you.
Great. And while we wait, we want to invite you to celebrate the life of an important member of our DART team. Pulling off extraordinary events requires extraordinary people. And Ray Harvey was just that. A leader, an engineer, a friend. Ray devoted his life to making the impossible possible. Tonight, we pay tribute to DART's former mission operations manager.
Ray Harvey was our mission operations manager for DART, but I've known Ray since I've been at the lab, which is about 14 years. As a young engineer, having people like Ray was actually extremely important because you could go ask Ray a question, he would tell you a joke, but he would also give you an answer, so you didn't feel awkward asking questions. You would just feel good coming out with more knowledge, but also you had fun in the process.
I've known Ray probably since I started working here almost 25 years ago, and he was always like a good mentor and a sounding board for anything we were doing. I think everybody learned something from Ray, his leadership skills, how to treat people, how to work as a team.
Ray was a pretty amazing person. Even though he was fighting this terrible disease, he made it a point to be involved in all the rehearsals and all the activities going on DART. He led the mission operations team to the last few days of his life.
He was really hoping to make it to the end of this mission. He meant so much to this team and to getting us to this point.
It represents so many years of hard work of him and also the team, but him leading that team. And so the DART spacecraft is a tribute to Ray.
We are hoping that this experience kind of goes out to Ray and to his family. We will really miss him, and we already miss him.
Ray has touched so many lives. Even in the short time that I knew him, he was so generous with his knowledge, and he made you feel like you belonged. Ray, you will be greatly missed. This one's for you. Tahira.
Thank you, Samson, for that beautiful dedication. Now, if you're just joining us, we're under an hour away from the DART spacecraft's head-on collision with asteroid Dimorphos. DART's mission is a test of a planetary defense technique that could one day save humanity. Rest assured, the test poses no threat to Earth. The spacecraft is almost 7 million miles away from us right now, and you're watching a live stream of its approach to Dimorphos. It takes about 45 seconds for the images you're seeing in the DART cam to make their way back to Earth. Any moment now, we should learn if DART is ready to commit to impact. While we wait, I'm here with Andy Rivkin, DART Science Investigation Lead, and Mallory DeCoster, DART Impact Modeler. Andy, Mallory, while we wait to learn if DART is ready to commit to Dimorphos, I can't help but wonder, why this asteroid?
That's a great question. The way that the double asteroid redirection test was designed, it was to measure the period change in a binary asteroid system. So we needed a binary asteroid, so that eliminates some number of objects. We needed something with a moon that was small enough that we could move it with a strike from a spacecraft, but not so small that we wrecked the moon. So when you kind of tick off all the possibilities, Dimorphos really ended up as the best choice and really the only choice that would provide a mission in this time period.
See, I want to go back to that. You mentioned having a moon that we could push but not destroy. Could you, now in pop culture a lot, we see that, oftentimes the idea is to just totally try to demolish the asteroid. Why have we chosen to not test that technique this time?
Yeah, the conventional wisdom for planetary defense is that you don't want to disrupt an object and blow it into a zillion pieces, but you want to keep it intact and just move it all as one piece. Because if you move it all in one piece, then you can keep track of it a lot easier. If you blow it into a million pieces, then some of them might still Earth, and you don't want to miss a thing.
Yeah, we might have more issues then. So we know that we have the perfect test subject. Mallory, now can you help us understand how, if mission success, DART's mission tonight can help improve models for mitigating hazardous asteroids in the future?
That's exactly right. So we stand to learn a lot from this DART impact. DART is both a technology demonstration as well as a really big science experiment. So from a technology standpoint, we're going to see if we have what it takes to autonomously navigate a spacecraft into a relatively small celestial body, something the size of a football stadium. That's pretty far away from Earth. From a science perspective, we get to perform one of the largest and fastest impact experiments that man has done. Something that could never be accomplished in a laboratory here on Earth. So we're going to learn how these large sizes, these fast impact velocities, and also these sort of extraterrestrial asteroid materials respond to deflection.
Wow, I mean, there's so much about tonight that we don't know, and it seems like your fun is just getting started, right, until after impact. So Mallory, Andy, thank you so much. And tonight, ground-based telescopes aren't the only one watching the action. A small cube satellite built by the Italian Space Agency was deployed by DART 15 days ago and has been in the area to give us a bird's-eye view of impact. Here's more on Licia Cube.
Licia is a 6U CubeSat of the Italian Space Agency participating in the DART mission, and it's also the first Italian satellite operating in deep space. Licia Cube mission objectives is to support DART in documentation of the impact effects, in particular in terms of the ejecta of materials that will be released from the asteroid surface after the impact, and also imaging the non-visible side of the asteroid during its flyby.
LiCiaCube will acquire images using its two different cameras, Leia, a panchromatic camera, and Luke, an RGB camera. Therefore, we can better understand the nature of the asteroid Dimorphos impacted by DART. By means of our Scientific Operations Center in SSTC ASI, we will distribute and process the images in order to make them available to the entire team.
We are here in Argotech's Mission Control Center in Turin, from where, together with ASI, we monitor the status of LiCiaCube. The batteries are charged, the radio is communicating correctly, and the navigation altitude is on the right trajectory. Everything is ready for the most important part of the DART mission, the impact with the asteroid.
DART is a global effort to prepare humanity for the unthinkable. Before the spacecraft can complete its mission, the autonomous navigation system must first confirm a lock on target. This is a key milestone that we should be hearing about soon. So let's go back to Samson for the latest from mission operations.
Hey Tahira, we are less than 50 minutes out and we just heard big news. We have reached the point where SmartNav is now target locked onto Dimorphos. That progress bar should move to your right that much further, closer to impact. Very exciting. In the meantime, joining me is someone who worked on the instrument, playing a starring role with this major milestone and basically all the way up to impact. Lisa Wu, mechanical engineer who helped install the Draco camera and built its cover. Lisa, thank you for joining me.
Thank you for having me.
So we just heard big news. We hit this target lock. It could have come fairly later than this, but we're in a good spot with this target. How are you feeling?
I am so excited. I'm sure the entire team is ecstatic. This is what we've been working so hard for in these very last moments, and we just heard we got target lock, so could not be feeling any better.
Very exciting. I mean, we are humming along. So a quick recap, SmartNav is DART's autonomous navigation system. It's been called the brains of the spacecraft. And right now it's essentially maneuvering that spacecraft on its own, as it will be for the last 4 hours. But Draco Imager, it's providing SmartNav with that unflinching view of Dimorphos, about an image per second. It is the eyes of the spacecraft. Lisa, what makes this camera perfect for this mission?
Yeah, of course. So the Draco instrument is a very, very high resolution, narrow field of view telescope. The image quality, let's go back. Draco is a descendant of the Mallory telescope, which might sound familiar because it took the very first pictures of Pluto on the New Horizons mission, which also might sound very familiar because that is an APL-led mission. So if you've ever seen the first pictures of Pluto, that is the amazing quality that we have on DART.
That's incredible heritage. And yeah, anyone who saw those images of Pluto, those were amazing, and that kind of ups the ante for what we're going to see with these pictures of Dimorphos, right?
Oh, yeah.
So we all know about, a lot of us have smartphones with, cameras. We have cracks, we have smudges. How did your team make sure that this camera made it in pristine condition to get to this point?
Of course. So our flight hardware, including this instrument, was made in the clean room. Very, very high clean facility. In order to make sure that the telescope works, we had to put it through a lot of electrical testing, optical testing, alignment testing. We had to make sure it performs as we intended. And then not only that, you have to take this instrument and put it through all the environments that it will see through space. So we put it through vibration testing, thermal vacuum chamber testing, all to make sure that it performs and it will survive through space.
That's amazing. Test, 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 and test again, right?
Yes.
This is how we get to a stage like this. That is
exactly
awesome. That is great. Thanks so much, Lisa. The number of astounding technologies that are on board this spacecraft is amazing, but doing the impossible requires nothing less than the astounding, right? All right, Tahira, we have the technology. Clearly, we have the talent. Now we wait for history. Back to you.
All right, thanks, Samson. It feels good to know that we have locked on target Dimorphos. Now, earlier we asked you to send in your questions by using the hashtag Planetary Defender. And I am joined now by two real-life planetary defenders. We have Kelly Fast and Lucas Paganini, both from NASA's Planetary Defense Coordination Office. Let's dive into what you want to know. So Kelly, Lucas, before I get to social media questions, we actually have a special question from a familiar face, especially if you're into football. So let's take a moment and hear from him.
What's up? I'm Joshua Dobbs, quarterback for the Cleveland Browns, and I have a question for NASA's DART team. On the field, I have to use precision passing in order to get the football in the hands of my teammates, and at least I can see where they are. For NASA's DART team, how are you able to aim a spacecraft at an object so far away?
You know, that's a really good question, Kelly, and I mean, we haven't really done this before. How can we aim?
Right,
well,
but I have to say, Joshua does in a few seconds what we've taken, years to do. Just as he has to throw it where he knows that the player will be, throw his football where the player will be, DART needs to end up where Didymos and Dimorphos will be. And so that was learned from astronomy, looking at through telescopes, calculating the orbit, and then the people who launched DART to its destination navigated there. So there's just a lot more calculations involved, which Joshua does in his head.
Yeah.
And then there's this autonomous navigation. It would be like he had a football that could navigate itself. Yeah. And so we have that to lean on that he doesn't. And so that's what helps get to that destination.
All right, nice. I mean, it's very impressive. And so we have another question from Jonathan on Facebook, who wants to know, how can a small satellite like DART be able to impact something as big and heavy as an asteroid and actually move it?
Right. And it's all about momentum, right? We have this tiny asteroid of about 160 meters, the size of a football field. And then you have this spacecraft, which is about 500 kilograms. So it's all about momentum, right? You have this massive asteroid and this tiny spacecraft. And how do you move it? It's all about mass and velocity. Since we don't have enough mass in that spacecraft, we have to really impact it hard, and that's why we're impacting it at 4 miles a second, which is outstanding.
Which is amazing. And I mean, we're actually going to get to watch impact live take place. And so that gets me to my next question. We have Metal Money on Twitter who asks, what is the size of the blast on the asteroid? Kelly, could you explain a little bit about that?
Well, and that's something that we're hoping to find out from this mission, because there's physics and calculations, but actually when you're dealing with a real asteroid that we haven't seen close up before, and what type of material might be on the surface, what the structure is, this is something that, like Lichia Cube, we hope to see as Lichia Cube flies by, to see what that blast was, how large it was, which will help those who are doing the modeling of how effective the impact was, and in changing the orbit, what all figures in, what Lucas just talked about, the mass and the velocity, but then also maybe that blast that is seen afterwards, the plume of material that we're hoping to see from Lichia Cube.
So how does tonight's mission play into the work that y'all do in NASA's Planetary Defense Coordination Office, Lucas?
Yeah, I would start by saying that this is a very important test. We're going to know if this kinetic impact is an effective technique to use in the case that there would be any potential asteroid en route to Earth. So definitely, for me, that's the most important thing about this test.
But then on top of that, there's finding the asteroids, because you can't go out and mitigate a possible threat if you don't even know it's there. And so NASA is very focused also on finding near-Earth asteroids with telescopes that survey the skies every night, looking for near-Earth asteroids, getting the orbits calculated, figuring out where they're going to be in the future to see if we even need something by DART, and then working to speed that up. NASA's working on the Near-Earth Object Surveyor space telescope that would look in the infrared and have a different perspective, complement the ground-based telescopes to accelerate things, just so that we know, is there a threat out there that we're facing that we do not yet know about?
Wow, I mean, it's incredible just to know the work that is already being done. It's good to know that we're building off of it, but it's good to know we've already got some people watching the skies. Yeah. And so I have our next question from Alan on Twitter, who asks, how long does it take for pictures to reach Earth? Kelly.
Well, the time it takes light and then a radio signal from the spacecraft to come to Earth is 38 seconds, but then there's also the time needed to process the images, so a few more seconds on top of that. So under a minute, but still it's not instantaneous because it's a ways out there.
Well, that makes sense. I mean, but under a minute to get something back from space, I'd say we're doing pretty good right there.
That's right.
So Lucas, Kelly, thank you so much for everything that y'all are doing to keep our planet safe.
Thanks, Tahira.
And so it's important to note that tonight we're attempting something that's never been done. And with that presents many challenges to overcome. Here's what makes DART a first of its kind mission.
The DART mission is a very difficult mission because we are trying to do something that hasn't been done before.
This is the first time we're going to an asteroid that is this small, this dark, and we're actually going to attempt an impact.
The DART mission is really something that the whole world can get behind.
We're doing this mission to prove that we can deflect an asteroid if we find one that is on an impact course for Earth.
We are trying to hit an asteroid 163 meters wide, which is about the size of the Washington Monument, while flying at 6 kilometers per second, which is like going from New York to DC in about a minute.
There is no chance that this asteroid could ever hit Earth.
It's a very small asteroid. It's only about the size of a small football stadium, and it's almost 7 million miles away from the Earth. That's 28 times the distance between the Earth and the Moon.
There's kind of a limit on how much mass you can launch into space. You know, rockets are only so big. So our spacecraft is only the size of a golf cart.
Draco is the primary instrument on the DART spacecraft. It is the camera that is going to be imaging the Dimorphos system as we approach.
When we first see the asteroid through Draco, it's just going to look like a pixel.
There's a star tracker on board that takes images of the stars and compares them to a known catalog to determine which way it's pointing in space. It poses the biggest risk because very, very small errors in this measurement can spell the difference between success and failure. And those measurements are going to be fed into the SmartNav algorithm that's going to be making the autonomous course correction commands that will put us on an intercept course.
There is a very small probability that we don't hit the asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, we're finding the asteroid, even then, we might still miss.
We're trying to teach a computer how to recognize an object we've never seen before.
And the way it does that is by taking pictures of the asteroid and then interpreting where it is in space and guiding itself to it.
The spacecraft is controlling itself. SmartNav is guiding the spacecraft. And we have very limited ability to respond in that time. So it has to do it all by itself.
And at about 2.5 minutes out, we cease all maneuvering and we coast until we hit the asteroid.
It is going very, very fast towards the asteroid, traveling at 6 kilometers per second.
200 times faster than a car on the freeway. So when we hit, all of that mass, all of that momentum pushes the asteroid.
Even giving it a small nudge will allow it to change its course.
But if we did see an asteroid on track for Earth, this would be enough of a deflection.
It's like a bittersweet moment. Yeah, all this hard work just got destroyed, but that was exactly why we put it all together.
Of all the endeavors that we do for space and in space, this is probably one of the ones that one day will be the most important thing that we've ever done.
In the future, I hope that DART can teach us what ways work and what ways don't work for planetary defense.
Because it is humankind's first demonstration that we have gained the knowledge and the technology to be able to protect the Earth from an asteroid impact.
Space exploration is rooted in pushing past boundaries. Remember, tonight is a test, and we hope to make impact. Now that you've learned of the challenges today's test, let's head back to mission operations and get a status update on DART's real-time progress. Samson, how are we looking?
Hey Tahira, we have 30 minutes to go until impact. As we heard earlier, so far so good. SmartNav is now targeting Dimorphos, thrusters are firing, maneuvering the spacecraft. Draco, Dart's eye, playing paparazzi with Dimorphos, providing SmartNav with about an image per second. And this is a good time to remind you that what we're seeing on the Draco feed is delayed by about 45 seconds on account of signal delay and image processing. And coming up, we're about to see the team conduct a final poll, one last scheduled confab to make sure that all systems are go. And as we head to that, I have someone with me who knows a thing or two about ensuring spacecraft readiness and integrity. Betsy Congdon, DART's mechanical systems engineer. Betsy, thank you so much for joining me.
Thank you.
So you led the team that literally put DART together, is that right, Betsy?
Yeah, so my job is to make sure the engineers and the technicians all physically put all these boxes that you've been hearing, bolts and all onto a spacecraft all together.
I gotta ask, with a mission so ambitious, how many hours, how many years, how many people? Do you have any idea at this point?
Oh man, so I mean, DART has been thought about for a long time, but really started in earnest about 5 years ago. We started building up the spacecraft, and in that assembly that I was talking about 2.5 years ago. And so it's been hundreds of hours, to make something like this possible. People with all sorts of talents. You've seen a lot of them today.
That's incredible. And so we're heading up toward another status update, as I said earlier. And as we all know, space is a unique and challenging environment. When you're assembling DART, what were the key boxes you were checking off of that very long quality assurance list to get the spacecraft to where it is right now and hopefully till impact?
So space is very hard, and so what we do is each individual component, Lisa was talking about this earlier, goes through its own individual testing, and then we put the whole spacecraft together, and we will check out the electrical systems, making sure all the boxes are working and talking to each other. We put it into a vacuum chamber, make sure it's going to work in space, put it through all the different temperatures it's going to see, and then put it on a shaker table and actually mimic launch. And so it actually goes through all of that as a full spacecraft as well as individual components. So we go through a lot of testing, mission operations, mission simulations to get to this point.
That's incredible. I mean, I don't know if you included, you mentioned so much array. Is that also accounting for the temperature fluctuations in space? That's another key part.
Yeah, so we have chambers here at APL that are specially built to take these spacecraft, put them into the vacuum of space, and run them through the temperature spaces that we're going to actually see.
It's incredible. How many times do you check? Is it like one test and we're done, or are you sometimes testing and testing?
Lots and lots of testing, and that's what makes it, so perfect. We're seeing these great images coming in because of all that testing and all of that work. So, you don't do anything once. You're doing it many times because once it's in space, there's not a lot of ways to fix it.
Right. Well, do you ever, think about that one panel, that one component that gave you a little bit of heartburn in the clean room, and you're up at night thinking, I think that thing is going to hold true up until the end?
Everything is looking really good. I will say, we had a lot of new technologies, which are really exciting. The ROSA solar arrays had never been integrated onto a spacecraft before, and so that was like a challenge, but one the team was up for, and now it's all ready and working perfectly.
All these new technology demonstrations, it only adds to the complexity of this mission and to, testing things. I wouldn't say even more so, but it's just as critical. But new technology, everything has to be so to make sure it comes.
Yeah, all of this new technology just requires extra testing, but that just gains confidence. You're seeing the team working through that, working through all these mission sims. So that's really what makes it exciting. You don't want to just do the same thing over and over. This is what makes APL a special place. We build these special spacecraft that, have never been done before.
Last quick question for you. It's got to be a little bittersweet that a spacecraft you poured heart and soul into is about to careen into an asteroid. How are you feeling about that?
I'm feeling great about it. It was designed to careen into the asteroid. It's meeting its destiny. So it's really exciting to see, and I can't wait for impact.
Well, it is serving a purpose. I guess that's why it's easier to let it go. Right?
Exactly, very much so.
That is awesome. Well, I think we are about to get into that final poll in the mock very shortly. So we're going to hear that final 30-minute poll, and then we're going to hear from Elena Adams again, DART's mission systems engineer, to give us that summary of what we just heard, how she's feeling, how they're feeling in there. Very exciting stuff. This will be the final poll of the evening. we are awaiting that final poll.
This is DART MSC on DT Mach. It is time for the last status poll. Yes. We're about, 7,000 miles from Dimorphos at this point, so yay. All right, image quality. How are we doing?
Still looking very good. Dimorphos still tracking along that same brightness predict as Didymos.
That's great. All right.
Maneuver complete.
Yes, thank you. All right. SmartNav.
SmartNav is looking nominal. We are at under 30 meters of projected miss distance right now.
Yeah, it's looking really good. Look at that. That's looking fantastic. Very excited. All right, GNC.
Yeah, GNC also looking good. We've been very excited to do those burns, so we've been waiting a long time.
Oh, this is great. Autonomy.
Autonomy is green. The heaters are cycling nominally, and we've had no new fault rules firing.
Okay, wonderful. DSN.
DSN is green, and ESA is green. Got plenty of margin. Looks good.
All right, ground systems.
Ground system has been helping a few users manage clients, but everything is going fine there, and we are green.
Yes, wonderful. Thank you, guys. Completes the poll. Last one. All right, so Didymos is looking like itself. We'll see what Dimorphos is looking like soon. In the meantime, we're going to transition to precision lock at 20 minutes. That's our next milestone. So thanks all.
All right, we're about to hear from Elena Adams from the Mission Operations Center.
Hi, Samson.
Hi, Elena. That sounded very positive. How's it going in there?
Oh, it's going great. It's going great. We've locked on Dimorphos. We're maneuvering towards it, and yeah, everything is looking really good. We were at the time of the poll within just a few meters of projected miss distance, which means we were hitting towards the center. And at this point, we're coming back there about 30 meters off the center of the lit portion of Dimorphos as of right now. We've executed 2 burns. And everything's looking on track.
Oh, that sounds wonderful, Elena. Thanks so much for that, and good luck on the final stretch.
Thank you. Have a good one.
All right, Betsy. We had that very positive poll, lots of fantastics, lots of clapping. We heard Lena in a very positive mood. How are you feeling?
I'm feeling great. It's amazing to see the actual dots on the screen for real coming down from the spacecraft.
Very exciting. Any words of encouragement for the team?
I mean, obviously, they're doing a great job. They've practiced a ton, and we're ready. Go DART.
You've heard it all loud and clear, Tahira. All systems are go, and we remain on track for impact. And like Betsy just said, go DART. Back to you.
All right, what an exciting update, Samson. You just heard it. All systems are go. Mission operations confirm the spacecraft is on track for impact. But in order to hit the mark, the test must first locate its target. That's why Johns Hopkins APL engineer Michelle Chen helped develop new autonomous navigation techniques that will ensure a bullseye. Let's take a look.
Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen, and I lead the team that is responsible for the autonomous navigation of DART spacecraft to hit an asteroid. The DART mission is the first planetary defense test mission. Our goal is to hit and impact an asteroid to understand and study the momentum transfer so that we could potentially later down the road, if we need to, deflect an asteroid on its way to Earth. I am the SmartNav lead. SmartNav stands for Small Body Maneuvering, Autonomous Real-Time Navigation. SmartNav, I always consider it sort of like the brains. And so the camera, Draco, is essentially the eyes. The algorithm has to identify and hit the target in the field of view of the camera. We're flying at over 6 kilometers a second. It essentially occupies a pixel up until possibly 30 minutes prior to impact, and then that's where everything gets really exciting. And so you could just imagine if it was a human being joysticking this. Because we don't know for sure what the asteroids look like, our simulation gives us the capability to use different asteroid shapes and asteroid objects to see that our SmartNav algorithm performs against all these unknowns. We're super excited and nervous as well. I love pushing the boundaries, and I love the application of math into real-world problems, and then seeing it actually doing its thing. To me, there's nothing cooler than that.
If you're just joining us, we're about 24 minutes away from DART's impact with asteroid Dimorphos. The spacecraft is flying at 4 miles per second, guided only by its autonomous navigation system. I'm here now with Tom Statler, DART program scientist, and Don Graninger, DART impact modeler. Tom, Don, thank you for being here with us tonight. We have some good news happening, but we did just hear about the challenges that DART is facing tonight. So Don, could you tell us a little bit about what kind of uncertainty exists with a mission like this?
Yeah, sure. So what's really interesting is that until just, even a few minutes ago, I feel like we're just getting our first looks at Dimorphos. And so we have absolutely no idea what we're going to be impacting into. It could be covered in rubble pile. It could be just a completely different shape. We don't know until we really write upon that impact. And that's probably one of our biggest uncertainties on this.
I mean, but that's what really makes tonight so exciting. And so, Tom, could you expand a little bit more on how we will use this information in the future if all goes successfully?
Well, this test is really important to understand how we might be able to deflect asteroids in the future. And when we measure the change in the binary period of Dimorphos, and we will understand how the asteroid reacted to our kinetic impact. And then as we get deeper understanding into exactly what the geology was of that asteroid, that's the basic information that's going to help us refine our physics understanding of asteroids and our ability to compute and predict, like Don does, run these fantastic codes and extend this knowledge to really have a good plan for how we might react if we ever do discover a dangerous asteroid that is different from Dimorphos.
Well, hey, I mean, it's better to be safe than sorry. So it sounds like y'all's party is really just getting started after impact. So congratulations on your success so far. It has been a pleasure. Thank you so much. Now, any second, we should be learning if DART has a precision lock on its target Dimorphos. This is a key milestone critical to tonight's success. Samson, mission operations must be buzzing. How are things going?
Hey, Tahira. The energy is indeed electric, and the team is hyper-focused. You could hear a pin drop right now as we're coming up on the critical 20-minute mark from impact and expecting to hear from the team that SmartNav is now precision-locked onto Dimorphos, which means that SmartNav will be tracking only Dimorphos from here on out. Why? SmartNav has full confidence that we are in fact tracking Dimorphos, and so we want to remove any confusion by continuing to track Didymos. Because what could happen with Didymos is that its shape could be such that there's a lot of shadowing, which could make it seem in the Draco imagery like multiple blobs, as the team likes to call them. And we don't want SmartNav to mistake any of those blobs for Dimorphos, so we're doing away with tracking Didymos altogether. We are waiting for that announcement of precision lock. All right, we're about to hear from the team. Actually, we have some time until we hear that. And now let's listen in for that confirmation of precision lock.
All right, we expect to be in precision lock soon.
are waiting for confirmation of precision lock.
MSC, this is SN5.
Go ahead, SN5.
We are precision locked and still tracking Dimorphos.
Yes.
We are soon going to hear again from Elena
All right.
Adams.
This is great. This is DART MSC on DT Mach. So this was our last milestone. At this point, we're going to be working towards Dimorphos. I expect we're going to do some burns. We're about 4,500 miles away from Didymos and Dimorphos, so let's see what happens.
Ground star 41, FC2.
Right, joining me now to react to that bit of good news is Lindsey Johnson, NASA's Planetary Defense Officer. Lindsey, you heard Lena, we are now precision locked, a lot of applause, things are looking good. And we are now headed for the moment of truth. How are you holding up?
Oh, I'm doing great. The team's been doing great. The spacecraft's doing great. This precision lock, is absolute milestone for the terminal phase here. We've got a good signature on Dimorphos, so the spacecraft has what it needs to guide itself in for the impact here in 17, almost 18 minutes. So we're doing great.
Yep, so close. Very exciting moments ahead. Now, we can't say this enough, and I know you've said it so many times, but it's worth repeating for viewers that Dimorphos is not a threat to Earth, nor will it be after impact, right?
No, that's right. This asteroid system is still almost 7 million miles away from the Earth. It's at its closest point in the orbit right now to Earth. So from this point forward, it's going to be moving away from Earth. So there's no chance of anything here. We've got to look for all the other unknown asteroids out there still to find what the hazard really is.
Thanks so much, Lindsey. I'll catch you on the other side of impact.
Okay, if you can.
Back to you, Tahira.
All right, thanks, Samson. It is amazing to know that we have a precision lock on target Dimorphos. Now, we have a fun way for you to join our mission, and it is by signing up to be a planetary defender. Visit bity.com/planetary defender. Take the quiz and receive a certificate like this one. Now, once it's official, show us on social media using the hashtag Planetary Defender. Now, telescopes from around the world are observing tonight's impact to ensure that how successful we are at changing the asteroid's orbit. They'll be measuring this success. And you may be wondering, how does that happen? Let's go behind the scenes with astronomer Nick Moskovitz at Lowell Observatory, home to the telescope that discovered Pluto, to see what's in store for DART.
This is Lowell Observatory. Lowell is one of many observatories around the world that will be observing the DART impact, NASA's first ever planetary defense test mission, to see how much a spacecraft impact can deflect an asteroid in its orbit. This is where Pluto was discovered, and we are still doing research in all areas of astronomy today. So let's go check it out. This is the Pluto telescope, the telescope that was used to discover Pluto almost 100 years ago. So here we are at the Clark telescope. This is where Percival Lowell sat to observe Mars. Let's head on over to the Lowell Discovery Telescope about an hour south of Flagstaff, which is where we are going to be collecting data for the DART mission. The reason we're all the way out here in the middle of this forest is that we have really dark skies here. And this is the Lowell Discovery Telescope. This is what a 4.3 meter telescope looks like. This is what we will be using to study Didymos and Dimorphos in the days and weeks after DART impact. The DART spacecraft will be hitting an asteroid called Dimorphos. It's special because it's a binary asteroid, which means a satellite around a larger asteroid called Didymos. And DART will actually be hitting Dimorphos. And what we will be measuring is how much DART changes the orbit of Dimorphos around Didymos. So this is an important test for planetary defense mitigation strategies in case we ever have to do this for real. The Lowell Discovery Telescope is one of many telescopes around the world which will be used to study Didymos and Dimorphos. It's really a global coordinated effort. And what we're looking at here is a large 4.3 meter primary mirror that's in the middle of the telescope tube here. Up at the top is a secondary mirror. The secondary mirror up top there is what is focusing the light down onto the instruments and allows us to take images with the camera that's located down at the bottom. This is maybe one of my favorite hidden rooms at the telescope. We're like standing inside the telescope, underneath the telescope, 100 tons above your head, held up by this and this, which is cool. It's sort of, as you can see, the highest peak around here, just over 8,000 feet. I come up here for sunset, because sun's setting right there, it's perfect. For DART, we're going to be collecting images of the night sky. And typically an observer would be here in front of one of these consoles controlling the instrument and taking images like these as they're coming in off the telescope. DART is really a sort of before and after experiment. We need to understand the system before the spacecraft intentionally impacts, and then we have to understand what the outcome of that impact event is. As we watch from the Earth, Dimorphos will pass in front of Didymos and behind Didymos. What we will be doing with those images is measuring the brightness of Didymos in those images and looking at how that brightness changes. And those dips in brightness allow us to measure when these eclipses happen and measure the orbit period of Dimorphos. And so you have essentially a fixed star field here. All the white dots are stars of different brightness. And moving through this field is Didymos and Dimorphos, which again, we can't distinguish them as discrete points of light, but we have that small object moving through the field of view. So after impact, we will then be able to go back and start observing intensely, looking for those mutual events, those eclipse events of Dimorphos passing in front of and behind Didymos. And on each one of these frames, we're measuring the brightness to assess whether or not it's undergoing one of these events where Dimorphos is passing in front of or behind, and using those to determine the orbit period of Dimorphos around Didymos. This is such a cool experiment. It's such a singular experiment. Using the ground-based telescopes like this one and others around the world to watch the system and see how it's affected by this impact event, because that's really what's going to give us the answer to what did DART do at the time of impact. And that will be exciting to see how that evolves over the days and weeks following that impact.
All right, after a 10-month, 470 million mile journey, DART is just minutes away from making history. A truly global effort, this mission has brought together people from around the world, united under one goal: to find a way to protect humanity from a hazardous asteroid if one were ever discovered. Now, usually NASA spacecraft are intended to operate for many years or even decades, but not DART. DART was built to be destroyed. DART is a mission of firsts, proving that a spacecraft can autonomously seek, find, and approach a target in space that's so far away we don't even know what it looks like. It also marks the first time humanity will have moved a planetary body in the universe. I said that correctly. Now, at this point, the spacecraft is controlling itself, making small maneuvers to ensure it's lined up with its target. DART is speeding through space and will cover the last 4 miles of its journey in just 1 second. Coming up, we'll hear the final updates from mission operators and witness the big moment live from space. Samson, you have the best seat in the house. How are we looking?
You're right, Tahira. Front row tickets to the biggest event in town, and things are looking good. We are T-minus 10 minutes to impact, and DART is precision locked onto Dimorphos and zooming down the home stretch. Now, we have a lot to cover in the time we have left, and I'm thrilled to have with me Lori Glaze, Director of NASA's Planetary Science Division, with me for the ride. Lori, such a pleasure to have you.
Oh my gosh, I am so excited to be here and really happy that we are here in this final 10 minutes. We are almost there.
Well, you were just in the thick of it with the team up until a few minutes ago. What is the atmosphere like in there? I can only imagine.
It's really, it's great. I mean, they're excited. Every time there's a marker that we meet a milestone, everyone is cheering and very excited. But there's also almost a sense of a calm confidence that with every milestone, everything's going, as planned. We're found and we locked on the target as planned, pretty much at the right time. They're looking at the brightness and the reflectivity of the object, and it's more or less what they expected. Everything is performing as expected, and so there's a lot of cheering and happiness, but just kind of a sense, hey, we've been planning for this a long time and we've got it.
We've got this, we've been planning for this. We can hear applause left and right throughout this evening, all good signs. What are they focused on at this critical juncture, Lori? It is basically years of planning, 10 months of making sure we get to this point after launch, and they've been juggling a lot. Is there anything in particular that they are glued on as we enter this moment of truth?
Yeah, so the main thing they've been watching is getting to that point where we could do the precision lock, where we had good enough signal coming back and enough confidence in where we are relative to Dimorphos that we could really do that precision lock onto the target. And it's hands off now, right? We're not, the spacecraft is going to drive itself, and really focused on that, that point where they could be precision locked. And they're also thinking about looking at and reassessing continuously what's the probability of miss, right? Mm-hmm. As you get closer and closer, that probability should get smaller and smaller, and it is. It looks really, really good right now.
Well, it sounds like the game of thinking, of wondering, really doesn't end until that last second comes to pass. So they can do a lot of great up until this point. We just have to see this through to these last few minutes. Well, and in a few minutes, speaking of that, all the years of thinking, of doing, planning, reacting is finally coming to an end. From 5 minutes to impact, there will be no more opportunity to send any commands to SmartNav in the Mission Operations Center. The team will be purely spectators, the data coming in, and they are just wetting it out like the rest of us for the first time. Lori, this is huge both from an operational perspective and also an emotional one, isn't it?
Yeah, it is. I mean, you can imagine, I'm really excited about it, and I've been engaged with this mission for the last 4.5 years that I've been in my current role. But this team has been working so hard on this for so many years, and they've put so much of their energy and their time into this, and so much planning and rehearsing, and it's a really big event for them to, like you say, just counting down and watching. At this point, there's not much else they can do but watch and see the fruits of all their work.
Yeah, I've gotten to know many members of this team over the past few months, and there's a lot of alpha individuals on there, right? You need a good mix of alpha people to make sure we get to this point. I can only imagine what they're feeling. Perhaps, like you said, a little bit of relief, a little bit of, can I let this go? I have worked for this moment so long, and now we can no longer do anything. That moment is just coming up.
Yeah, but I think they're ready. I think they're at that point. You're getting some shots of Elena Adams, the systems engineer, and you can see the excitement in her voice. She's so ready to show the success of this mission.
This is awesome. 5 minutes out, which we're coming up on now. The team will be hands off 2.5 minutes from impact. SmartNav, which has been guiding the spacecraft autonomously for 4 hours, will also step away, stop any maneuvers. DART will simply be coasting to its fate. This is blockbuster stuff, Lori.
Oh, yeah. Oh, yeah. We are there. Yeah.
I have front row tickets, and we are very soon about to open up these airwaves in the Mission Operations Center. We'll stay plugged in all the way through impact. Remember, at this point, 5 minutes out, no more commands to SmartNav will be possible. The team is watching it just like you and me and the rest of us. All right, we've reached 5 minutes from impact. The final command opportunity to SmartNav has passed, and the team is simply watching that data stream in just like we are. Also remember, there is a 38-second lag for the data to travel to Earth, and also an additional few more seconds for image processing. It's important to note that. should be hearing the chatter in the Mission Operations Center momentarily.
This is Dart MSC and DT Mach. 5 minutes till impact. 5 minutes till impact. We are at 1,100 miles away. Also, our window for sending any commands to the spacecraft is done. Contingency's done.
This is a great vibe in that Mission
All right.
Operations Center right now, Lori.
It really is. They are so excited. And
This is investigation
No,
one on DT
I'm
Mach.
honing in, looking at these images as we get closer and closer, and you look at Didymos, and just you're starting to see this physical body appear there. It's incredible, just incredible.
Great.
I'm still having a hard time believing this is real imagery coming in near real time.
Yeah. Yeah, but you've been watching it over the last, 30, 45 minutes go from just being a collection of individual pixels, and now you can actually see the shape and the shading and texture of Didymos, and we're going to see that same thing with Dimorphos as we get closer and closer. This is so cool.
Never
We're still
before seen
maneuvering.
images of Dimorphos will come into stark relief
Absolutely.
a few seconds before impact.
Didymos. It's amazing. All right.
The team is standing, just recognizing this moment, years in the making. It is really nice to see them relax a little bit, get off from those computers that they've been glued to, and just appreciate this moment that's coming.
Yeah, and they've earned this. It's just great to see them there. This is so cool.
Lori, we hit another major milestone. We are now 2.5 minutes from impact, and SmartNav has stopped maneuvering the spacecraft. DART is now coasting toward Dimorphos, and we hope into the history books.
Absolutely. This will be, I'm sure you've heard it many times tonight, humanity's first ever attempt at trying to move another celestial body, and also our first attempt ever to execute a mission in sole purpose of planetary defense. So what an exciting, exciting time. Yeah, and I'm starting to see Dimorphos start to come into view there. You can see it starting to take shape. I'm starting to see individual boulders on Didymos. Unbelievable. Unbelievable clarity of images there.
We're coasting on in. Our projected miss distance is going to be about 17 meters.
All right.
All eyes on this event. Space telescopes, ground telescopes from every continent on Earth.
Yeah.
Yeah.
All right. 2 minutes out.
Does not look like one single rock to me.
Oh, boy, we're getting close.
14,000 miles per hour, Lori.
14,000 miles per hour, and remember, 45 minutes ago, 55 minutes ago, we couldn't even resolve this object in space, and now we are, you can see us zeroing in right on target.
And we're now dropping the clock, and we'll go by loss of signal to confirm impact.
Right. Yes. Imagine we'll get that loss of signal, and then we'll hear from Elena Adams again, and letting us know that we've been successful.
I feel like that'll be a crystal clear signal.
I think so. I think we're starting to see more resolution. In fact, look at that. Didymos has even gone out of the view. We're now just seeing Dimorphos.
This is remarkable stuff.
Oh my goodness, look at that.
Looks like control system settling down. Angular rates look really good. I think we're going to get the investigation team some good pictures.
Wow.
No, come on, we can do better than that.
Yep. Starting to see those individual boulders there. We can see shadows of the various rocks on the surface.
Impact. It's amazing, guys. Oh my goodness, look at that. Unbelievable.
Yeah. Looks to me like we're headed straight in. Oh my gosh. Oh, wow.
Yeah. my goodness. 8,
Yeah.
7,
Oh,
6,
wow.
5, 4, 3, 2, 1.
Oh, wow.
Awaiting visual confirmation.
All right. Let's see. We got it? Waiting.
And we have
Every
impact.
minute.
A giant leap for humanity in the name of planetary defense.
Woo. Fantastic. Oh, fantastic. Oh.
What a moment. Very few words can really capture this moment. This is beautiful to watch. Amazing.
What a team. What a team and what an accomplishment.
Team. A few weeks ago, they had their last dress rehearsal. They were getting emotional at the dress rehearsal, and they're like, this is crazy. We're getting emotional. This is not the real thing. I can only imagine what they are feeling right now.
Yes. Well, you can see them there on screen. They're all pretty excited. Wow.
Hearing impact, the curtains close on Draco feed. That raw joy from the team, years of hard work and the weight of expectation lifted off their shoulders. This is amazing. This is beautiful. And Lori, really, this is a huge moment for the mission. Lots more work needs to happen in the days, weeks,
Absolutely.
months.
Now, as I always say, it's one of my favorite missions. Now is when the science starts. It just starts now. Now that we've impacted, now we're going to see for real how effective we were. We're going to train all of those ground-based telescopes on the Didymos Dimorphos system, and we're going to make measurements that will help us determine just what its orbit looks like now relative to what it was before. So it's going to be great. Very cool.
All right, this is when science, engineering, and a great purpose, planetary defense, come together, and it makes a magical moment like this.
Yeah,
really.
Absolutely. And you can see so many people there that have made this happen. The team of APL engineers that have really poured their souls into this mission.
Lori, any last words to mark this historic moment?
Oh. We're embarking on a new era of humankind, an era in which we potentially have the capability to protect ourselves from something like a dangerous, hazardous asteroid impact. What an amazing thing. We've never had that capability before.
Thank you so much, Lori. Those are poignant last words. Tahira, history has been made. Back to you.
Wow, I mean, what an exciting day for the DART team. And in case you're keeping score, humanity 1, asteroids 0. Now I'm here with Nancy Chabot, DART coordination lead. Nancy, talk about a moment to catch on camera. What is going through your head right now?
I mean, I'm just thinking, wow, that was amazing, wasn't it? I mean, those images, you just got closer and closer, and sort of we've been planning for this moment. We've been talking about it for years. At APL here, we've been working on this since 2015, and I knew, I've been talking, these are the images that we're gonna see, and they're gonna be spectacular. And I think even then they exceeded my expectations of just zooming in like that, and it really is just such the team accomplishment, and to get to this moment over so many years. And I don't have to talk about it as coming anymore. It's happened now. We have done this.
It's happened, and it is just incredible that as humans, we have done this, we did this. And Nancy, do you have anything you'd like to say to the teams who made tonight possible?
Oh, I mean, I don't need to say anything to the teams because I know everybody like me is really proud to be part of this, right? Proud of this thing that we've been working on for years, and even before 2015, internationally, people wanted to do this. People wanted to take this first test. And then we finally did. Partners across the United States. We have actually 28 countries represented on our investigation team of scientists, telescopes on all 7 continents, everybody doing their part to make this moment happen. I know I'm I'm really honored to be on this team, and I know other people on the team feel the same way.
As you should, Nancy. And I mean, there's a lot to celebrate here tonight. And so now that we have confirmed impact, can you let us know what's next for this mission?
Well, I mean, I think I'm still taking a moment here,
soak it in. I'm
because
sorry.
this is
Soak
a
it
big
in.
deal, and this was a really hard technology demonstration to hit a small asteroid we've never seen before and do it in such spectacular fashion. But I know other scientists on the team, like me, are already pointing at those images, being like, "Did you see that boulder? Did you see that smooth area? Did you see the shape? What does that mean?" And Lychee Cube is like flying by right about now. They're close approach, like taking images, and they're storing them, and we'll get those in the next days. Telescopes here and in space are looking. They're looking at the brightening of the rock that's thrown off from that spectacular collision that we saw. And this is going to go on for weeks. And so there's still a lot of excitement to come, but nothing to take away from this moment.
Yeah, this is just the beginning. It looks like everybody is celebrating here in Mission Operations. I think I just saw Bill Nye there. And so it is a huge day for this team, but also for humanity. You know, Nancy, you mentioned earlier about some of the international collaborations. And could you give us an idea on kind of the scope of DART's mission, right? It's not just us in the United States that's focusing on this. So can you expand a little on that?
Yeah, I mean, planetary defense is really an international issue. We are all on this planet together, right? I mean, and I think it's been so great for this mission to really support and embrace that international cooperation for planetary defense so that we can maximize what we learn. And this idea came about from international scientists talking to each other, working together, you know, in order to make this moment happen for NASA's Planetary Defense Coordination Office, building the spacecraft here at APL. But really, scientists around the world are ready to study the, what did we do to Dimorphos? But more importantly, what does that mean for potentially applying this in the future? I mean, DART really is just the start. It's just the first planetary defense test mission. It was spectacular, and it's accomplished, and we'll figure out how effective it was. That's really what we're going to learn in the next weeks to come. All right, we hit this asteroid. Now, how effective was that at deflecting it, and what would that mean for using it?
Yeah, there's still so much to unpackage here. And so we have a special guest who is wondering, you know, more of what's next for this big mission. So let's hear from her now.
Hey everyone, I'm Danny Hansen, American Paralympic rower and hydro athlete. And first, I would like to congratulate the entire DART team on crossing the finish line. So congratulations. And with that, here's my question. Now that DART has impacted, how will you know if the spacecraft has actually changed the asteroid's orbit?
That's a good question.
Yeah, I mean, so this is a double asteroid system. So all we've done here actually is change slightly how Dimorphos goes around Didymos, right? And the telescopes on the Earth have studied this for years. So we knew it used to be 11 hours and 55 minutes. What is it going to be now? And so the telescopes are going to measure that period change. And they're so good at this. They've done it for decades already to get us to that point. And they're going to work for the next weeks and make that measurement. And when we have it, we're going to be sure to share it with everybody to see how much we did deflect this asteroid with the DART collision.
Wow. Well, Nancy, I mean, it's time for you to celebrate. So congratulations on everything tonight, and go DART.
Oh, go DART. This was spectacular.
Yes. And so we have Samson standing by in Mission Operations with two very special guests. Let's hop over there and see what's going on.
Thanks, Tahira. I have the pleasure of introducing NASA Administrator Bill Nelson, who has a special message for us.
Hey, congratulations. Boy, the DART team, you really did this one very well. It's been a successful completion of the first part of the world's first planetary defense test. And there were years of hard work. There was a lot of innovation and creativity that went into this mission. And I believe it's going to teach us how one day to protect our own planet from an incoming asteroid. I really look forward to learning all about what's happening from the observatories so they can tell us about the changes in this asteroid's orbit. So thank you to this international team. We are showing that planetary defense is a global endeavor, and it is very possible to save our planet.
All right.
That was eloquently put, Administrator Nelson. Joining me right now are Deputy NASA Administrator Pam Melroy and APL Director Ralph Semmel. Thank you both for being with me. Pam, I'll start with you. How are you feeling having witnessed this historic event up close?
Oh, I was absolutely elated, especially as we saw the camera getting closer and just realizing all the science that we're going to learn. But the best part was seeing at the end that there was no question there was going to be an impact, and to see the team overjoyed with their success.
That's beautiful. What does this mean for NASA? What does this mean for planetary defense?
Well, NASA works for the benefit of humanity. So for us, it's the ultimate fulfillment of our mission to do something like this, a technology demonstration that, who knows, someday could save our home.
Very powerful. Thank you, Pam. Ralph, you were in that mock for the moment of impact. We've seen a lot of major milestones in APL's history in space. We're talking the first flyby of Pluto, the first mission to orbit Mercury, and now the first spacecraft to impact an asteroid. What was the moment like for you in there?
It was incredible to see how so many years of hard work and creativity resulted in a direct hit of Dimorphos. Was just an adrenaline rush. I'll add that I've been at the lab now for quite a few years, and I've been involved in a lot of missions and achievements, and never before have I been so excited to see a signal go away and an image to stop.
Ralph, I'm going to give you both a treat right now. We're going to play that replay of impact on our screens right now so we can enjoy it again. Ralph, what does this achievement mean for Johns Hopkins APL? Huge, right?
Oh, it is huge. And in fact, if you'll excuse the pun-like statement here, the impact on APL, as it was on Dimorphos, is immense. This is exactly the kind of mission that APL seeks to do, a never-before-done mission. I'd like to thank NASA for entrusting us with this mission, and I'd like to tell everyone how proud I am of the entire DART team and APL for this game-changing achievement.
Incredible. Thank you, Ralph. And we're watching that replay right now on our screens and just admiring that remarkable achievement once again.
They were just tiny blobs of light, and now they are real objects to us, which is amazing.
Never before seen up until today.
That is amazing. You know, it's just as good the second and third time.
There's that drop off, knowing we made impact.
Fantastic.
Well, there you have it. A lot of pride here tonight, along with the promise of big things to come. And with a successful DART impact, that will do it for us today at the Mission Operations Center. Back to you, Tahira.
Amazing. I mean, today is a fantastic day. And DART is just the beginning of a global planetary defense effort. In 2024, the European Space Agency's Hera mission will conduct follow-up observations of asteroid Dimorphos and measure in great detail DART's kinetic impactor tests. Let's take a look.
The DART impact is going to be an incredible moment, something we've been looking for over 17 years. My name is Jan Carnelli, and I'm leading the Hera mission for the European Space Agency. The deflection by DART will be measurable from ground with telescopes. However, only with Hera coming up close and inspecting the asteroid will unveil all of those parameters that will allow us to plan for a deflection mission if one day we need one. This is the propulsion module of the Hera spacecraft that will take us to asteroid Dimorphos and will allow us to study the results of the DART impact. The propulsion module is being built here in Italy and then will be sent to Germany, where it will be mated with the instruments and the rest of the spacecraft to be ready for launch in October 2024.
We started designing and conceiving the whole mission and the spacecraft about 2 years ago, and we have a launch date to meet that is a fixed date in October 2024. So it's challenging, but we're making it possible. You could say that Hera is really 3 space missions in one. We have one, the main spacecraft that we are currently building at OHB in Germany, but we also have 2 smaller missions that are spacecraft in their own right. Those are the 2 CubeSats, Juventus and Milani.
The CubeSat I'm working on is Milani, which will perform spectral measurements and dust detection following the DART impact. My name is Margherita Cardi from TEVAC International in Italy. We will work alongside the other CubeSat, Juventus, which will perform kind of an X-ray of the asteroid to understand the internal structure.
This is going to be the first time that we have CubeSats on board an ESA spacecraft. Once we arrive there, we will be deploying the CubeSats in order to complement ESA's scientific observations, taking more risk, but also trying to have higher rewards.
The CubeSats will be installed on 2 panels that will be mounted on each side of the structure of Hera. They are just the size of shoebox, however they contain complex technology which will really allow to bring added value to the Hera mission.
Hera and DART represent a fantastic international collaboration between NASA and ESA. The 2 missions complement each other and will validate an asteroid deflection technique that we could use in the future to protect planet Earth.
There you have it. Tonight, we've ushered in a new era in planetary defense. At 7:14 p.m. Eastern, the DART spacecraft targeted and collided with Dimorphos, showcasing a technique that we could use if a hazardous asteroid is ever on a collision course with Earth. Even though impact is over, the process of moving the asteroid is still going on as we speak. Over the next days and weeks, we'll be monitoring Dimorphos from all angles, tracking its change in orbit with ground-based observatories, studying the impact crater and ejected materials with space telescopes, and we may even get images from missions like Lucy, Hubble, and Webb. Now don't miss a beat. For mission updates, follow Asteroid Watch on Twitter, NASA's Solar System on Twitter and Facebook. Remember, impact was just the beginning. Science and images will be rolling in soon, so stay tuned to nasa.gov/DART. We'll be back at 8 p.m. with members of the team to capture reactions and celebrate this historic event. So join us soon on nasa.gov/live. And for more updates on Artemis and rollback operations happening tonight at the Kennedy Space Center, head to nasa.gov/Artemis-1. Thank you for watching NASA's coverage of DART Impact from Johns Hopkins Applied Physics Laboratory in Maryland. We want to give a special thanks to all of our guests for participating in today's broadcast, and a big shout out to my co-host Samson Reiny for keeping us keyed into the action. Go DART, and good night.